Let's look at load cells. Load sensors measure mechanical force. The forces can be large or small, for example, weighing heavy objects or detecting low force tactile pressures. In most cases, it is the slight deformation caused by the force that the sensors measure and not the force directly. Typically, this deformation is quite small. Once the amount of tension, stretching, or compression, squeezing, displacement has been measured, the force that must have caused it can be calculated using the mechanical parameters of the system. The ratio of the force to deformation is a constant for each material, as defined by Hooke's law, where V is equal to Kx, where K is the spring constant of the material, F is the applied force, and X is the extension or compression as a result of the force. For example, if a mechanical part has a spring constant of 1,000 pounds per inch and it compresses half an inch under the load, then the load must be 500 pounds. Bonded wire strain gauges. The bonded wire strain gauge can be used to measure a wide range of forces from 10 pounds to many tons. It consists of thin wire, about 1,000th of an inch, looped back and forth a few times and cemented to a thin paper backing. More recent versions use printed circuit technology to create the wire pattern. The entire strain gauge is securely bonded to some structural object and will detect any deformation that may take place. The gauge is orientated so the wires lie in the same direction as the expected deformation. The principle of operation is as follows. If the object is put under tension, the gauge will stretch and elongate the wires. The wires not only get slightly longer, but also thinner. Both actions cause the total wire resistance to rise, as can be seen by the basic resistance equation R is equal to rho L over A, where R is the resistance of a length of wire, rho is the resistivity, L is the length of the wire, and A is the cross-sectional area of the wire. The change in resistance of the strain gauge wires can be used to calculate the elongation of the strain gauge and the object to which it is cemented. If you know the elongation and the spring constant of the supporting member, then the principles of Hooke's law can be used to calculate the force being applied. The resistant change in a strain gauge is small. Typically, it's only a few percent, which may be less than an ohm. Measuring such small resistances usually requires a bridge circuit, shown in figure B. With this circuit, a small change in one resistor can cause a relatively large percentage change in the voltage across the bridge. Initially, the bridge is balanced or nulled by adjusting the resistances so that V1 is equal to V2. Then, when the gauge resistance changes, the voltage difference, V1 minus V2, changes. The bridge also allows us to cancel out variations due to temperature by connecting a compensating gauge known as the dummy as one of the bridge resistors. As shown, the actual compensation gauge is placed physically near the active gauge so as to receive the same temperature, but it is orientated perpendicularly from the active gauge so the force will not elongate its wires. There is an example in the text that goes through the algebra involved in calculating the equations associated with the strain gauge. It's not difficult, just tedious. You should go through it to check your understanding, but the results are the following equations. The change in the strain gauge resistance is proportional to the voltage detected across the bridge. The strain of the object is proportional to the voltage detected across the bridge. And the ratio of stress over strain is a constant called Young's modulus. Take some time to read the text to see the origins of these equations, which we will now use in an example. A strain gauge and bridge circuit are used to measure the tension force in a bar of steel that has a cross-sectional area of 13 square centimeters. The strain gauge has a nominal resistance of 120 ohms and a GF of 2. The bridge is supplied with 10 volts. When the bar is unloaded, the bridge is balanced so the output is 0 volts. Then force is applied to the bar and the bridge voltage goes to 0,0005 volts. Find the force on the bar. Solution: first calculate the change in strain gauge resistance due to the applied force. Using the equations previously derived, we get a delta R of 0,024 ohms. Next, calculate the elongation, the strain on the strain gauge. So epsilon is equal to 0,001 centimeters per centimeter. Finally, E is equal to rho over epsilon. This will require looking up the value of the Young's modulus. From table 6.2, we find it to be 2,07 times 10 to the 7 newtons per square centimeter for steel. Rearranging the equation gives us a rho of 2070 newtons per square centimeter. This result tells us that the tension force on the steel bar is 2070 newtons per square centimeter, and because this bar has a cross-sectional area of 13 centimeters, the total force in the bar is 26,910 newtons. Strain gauge force transducers, called load cells, are available as self-contained units that can be mounted anywhere in the system. A load cell may contain 2 strain gauges, active and compensating, and a bridge. A typical application for load cells is monitoring the weight of a tank. The tank would be sitting on 3 or 4 load cells, so the weight of the tank is the sum of the outputs of the load cells. Another type of force sensor uses the piezoresistive effect of silicon. These units change resistance when force is applied and are 25 to 100 times more sensitive than the bonded wire strain gauge. A semiconductor strain gauge is a single strip of silicon material that is bonded to the structure. When the structure stretches, the silicon is elongated and the resistance from end to end increases. However, the resistance change is non-linear. Some applications call for low-force sensors. For example, imagine the sensitivity required for a robot gripper to hold a glass of water without slipping and without crushing it. Strain gauges can measure low forces if they are mounted on elastic substrates like rubber. Then a small force will cause a significant deflection and resistance change. Another solution would be to construct a low-force sensor with a spring and a linear motion potentiometer. The spring is compressed a distance proportional to the applied force, and this distance is measured with the pot. A very low force tactile sensor can be made using conductive foam. This is the principle used in membrane keypads, as illustrated. The conductive foam is a soft foam rubber saturated with very small carbon particles. When the foam is squeezed, the carbon particles are pushed together, and the resistance of the material falls. Therefore, in some fashion, resistance is proportional to force. At present, the concept has found limited application in such things as calculator keypads because of its simplicity and low cost. However, it's a viable option for other applications such as robot tactile sensors. Finally, a very small tactile sensor can be made with 2 or more limit switches mounted side by side with spring actuators that are set to switch at different pressures. As the pressure increases, the first switch closes. Then, with more pressure, the next switch closes, and so on.